Hi, everyone. Welcome back to session 3 of the Philosophy of Data Science series. Today, we're starting off what I expect to be about a 3-part conversation covering one of my favorite publication series. And in particular, in this case, it's on applying prognostic and predictive models to the medical domain. But I think that the value of the series isn't that it's only specific to medical domains. Where it's valuable is for anyone who is working in data science and looking to apply valid predictive models in any setting. I think what really highlights this series is that they bring you through the thought process of all the steps that are required to validate a predictive model. And it's written in very plain, tractable language, so that essentially, even if you're a beginning data scientist or an experienced data scientist, there's something in it for each of you. I first read this series back when I was starting my doctorate. And in rereading and reviewing this, the publications in preparation for this series, I found new things that I liked and enjoyed again. So I think that this shows that it is a very useful series. Our speaker today is Karel Moons, but other presenters on this include Patrick Royston and Doug Altman. I think I'm probably forgetting some people, but
Van der Vergouwen. Yep.
Yes. And I just have to say, obviously Doug Altman was one of who I think was one of the great scientific thinkers in statistics. Obviously, statistics can span a lot of methodological work, a lot of mathematical work. I think Doug Altman really stands out as one of the great scientists in statistics. And obviously,
I agree on that.
Yes, yeah, he was a great contributor to our field in many ways, and also, I personally find him to be one of the best statistical writers. Although I'm also biased because I tend to like the topics that he writes on. But Karel, you're here today, and we're just going to go through the series. The links to each of the publications is a 4-part British Medical Journal series, and we'll just go through and have a conversation about it. So, Karel, why don't you introduce yourself?
Thanks, Glenn, for the kind words. And let me first kick off by saying that I'm so happy that I had the privilege to work with a person who became my personal friend also for a long time, Doug Altman, late Doug Altman, which I think indeed was one of the best writers in statistics, not only because he is writing on the topics that you and I apparently are very much familiar and acquainted to, and also very much alike, but also on many other topics that is not so much close to my own expertise. He was such a clear thinker, but also a clear communicator and clear writer, both verbally and by the written word. Yeah, it's wonderful that a young person like me, still young, has had the privilege to work for 15 years with Doug Altman so closely. Yeah. But indeed, thanks for this interview, and interesting. I was very pleased that 11 years after date, this series still is so prevalent and new, and that you would like to ask me a few things about how that series come to the end, what you have seen in BMJ 2009. But my name is Karel Moons. I'm a clinical epidemiologist working at the Julia Center of the University Medical Center in Utrecht. I'm also affiliated with Vanderbilt University in Nashville. The previous head of the Department of Biostatistics is Frank Harrell, a personal friend of me as well, and also affiliated to actually the CSM at Oxford University, where Doug Altman was the head of.
Yeah, I'm a big fan of the output of CSM, obviously, although I am, of course, extremely biased. I'll say, actually, Frank Harrell, when you mentioned him, he's someone who I was actually hoping to bring on as a 4th person. So I might pester you after this because
you can.
Yeah, strong opinions on dichotomizing continuous variables.
For example, yeah.
Cool. So to begin, let's talk about this. The British Medical Journal and project called BMJ Series. It's a 4-part paper series. I believe it was published around 2009-ish.
Yeah.
What's nice, I wish more journals did this, where it's a cohesive series. Each of the papers is probably about 6 pages in total length. And it covers different parts of essentially the story of validating predictive models. This one focused on examples in the medical domain. But the fact is, these are applicable regardless of what
I agree.
domain you're working in.
Although I do have to say, of course, all the authors that were involved are medical scientists, so to say, biomedical scientists, all in the medical domain. But I agree with you. I think we also kick off. It is 4 papers, by the way, that series. One is what is actually prediction, prognostication in medicine, but we kick off in a more general concept. And the second one is what do you need? How do you develop a prediction model? Then the third one is how to validate, to test the accuracy, the value of the prediction model. And the final one, which is an interesting one and quite new, but very prevalent also in the discussion with AI-based prediction algorithms, which is now hot, of course, is to quantify whether they truly lead to improved effectiveness of our medical care system or patient outcomes, which means that you quantify the impact of the use of these models, which is different, very different from the preceding 3 models, which is more about the predictive accuracy of these models. And that's something else than the effectiveness of the models. But I agree, in paper 1, we explain what prediction is, and prediction is simply foretelling, foreseeing something we do not know yet. And we constantly do that in our life. Actually, even right now on the spot, we are predicting in our head without realizing it, how well will this interview go, or what will be the next question, what will be my next answer. We're constantly predicting. If we cross the street, we are predicting, am I getting there safely, by observing the traffic around me. Weather forecasting, COVID pandemic forecasting, whatever, economic forecasting, it's constantly prediction, something we don't know. And indeed, in medicine, there are 2 ways of prediction, particularly. One is the easy one, is prognosis, prognostication. There you're predicting an outcome in the future somewhere. And that future can be in minutes, for example, post-operative or intraoperative complications. It can be hours, post-operative complication, or IC, intensive care complication. It can be days, hospital days. It can be weeks, months, years, or even lifetime prediction. So that's prognostication, predicting in time, but that's prediction in time, it's prognosis, but it's also in diagnosis. The series covers particularly prognosis, but also diagnostic prediction models are very prevalent in medicine, and therefore, and there we actually predicting the result of a kind of gold standard test, a reference standard that we haven't done yet. So with simple parameters like symptoms, signs, and easy to obtain test results, you're predicting a more usually costly, invasive, or burdening test result. And that's also prediction because you haven't done that test yet. So in medicine, prediction is 2 things: prognosis, in time prediction. That's the series in the BMJ, but almost everything we say in that series also applies to diagnostic prediction models in medicine. I just want to emphasize that in this interview.
Yeah, that is something, that is one of the things I think pops out, where essentially 2 things I've noticed very much that really sort of distinguish this or clarify that the context is in medical domain. One is, of course, like the focus on things like, I wouldn't say hazard models in particular, but, that's sort of the survival curves issues. And then also classification. Whereas I think that, for example,
classification is usually what diagnostic refers to.
Yeah.
So the big difference between diagnostic prediction and prognostic prediction is time. With diagnostic prediction, you're predicting something that is already there yet, a diagnosis, but you haven't just measured it. And with prognosis, you're predicting in time, something in time. And when that time interval is long, we usually use their time to event models, survival models, you just mentioned it. And if that time period is short, then we tend to use, in medicine at least, logistic models. It doesn't become a classification model then, as with diagnosis, but it rather becomes predicting the probability that an event will occur in the next hours, in the next weeks, in the next month. Personally, if I'm going to predict beyond 6 months, I usually go to time to event models. But there's no golden rule in that.
Yeah, I think so. I guess where's one of the maybe we should just do this because this is very applicable to everyone. One of the main things I think that you're addressing this is the fact that people aren't using a lot of predictive models, even though, of course, the technology is there. The data is, I'll say there in quotes, because of course that's one of the issues that we want to discuss and sort of try to parse through. But the fact is that the uptake of a lot of these predictive statistical data science models is not where it could be, as it, if, compared to where if these models were more used because they're better scientifically validated. So I guess, maybe we should talk about that, about the sort of the gap between the hype in the use of these models and whether or not they actually get used and whether or not they're useful.
Yeah, it's particularly the hype, the big gap between the number of models that is being developed. And then there is a gap of the number of models that's being validated after their development. And then there's another even bigger gap, the number of models that is validated, but still not used into clinical practice or into daily practice. Yeah, that's two big gaps indeed. And yeah, as you have seen in that series, particularly in paper 1, we focus on what are the essentials of the data set and the design or the type of study that led to those data sets. What are the essentials that you need to address to make sure that the data set you use is valid for the predictive purpose that you have with your model? And the second paper again is then more about the aspects on how to develop that model with variable selection and dichotomization. You just mentioned that. And the third paper is about validation of these developed models. And the fourth paper is about the use of these models and their effects in daily practice. That's how this series is built up. And unfortunately, it was already at the time that we wrote that series, we saw that the number of developed prediction models in medicine is huge. It was already huge at the moment we wrote that series. Now that was in the early, I think we started, Doc Altman and I met in Australia, I remember it very well, and we concepted there this series, and I think it was 2006 or something. It took us 3 years to write the whole series because we submitted the whole series at once to BMJ. And at that time, we were simply struck by the fact, my goodness, everyone self-respecting statistician or epidemiologist developing a model. And now suddenly, or perhaps even every self-respecting biomedical research develops a model because we can. And it's pressing buttons. In the statistical programs, when Windows came in, it was pressing buttons. You didn't even have to write any scripts anymore. You just do it, and it gets out. If you have a data set, you get a model always, by definition. So the number of developed models was so huge, and then we were struck by the fact that only a few were actually validating that model in another data set from which it was developed. And let alone that someone even continued to show the effectiveness of using such a model in practice, and does it really lead to better patient care and better patient outcomes? Yeah, and sometimes it shocks me even more than it did in the 2006. Is that now with the data science, where actually everyone is going to develop a model because they can have access to data. The number of developed models is now even, it's almost overwhelming. It's ridiculous, as you might know, is that in the BMJ, by the way, for the very first time in the history of BMJ, as I've heard, is doing a living review. And every 6 weeks with a large international team, we are conducting a critical appraisal of all existing models predicting COVID-related consequences. So there are 3 types of COVID-related prediction models. 1, predicting who gets COVID. 2, the ones who have symptoms, do they really have COVID? Can you predict it early without having to do the invasive testing? And 3 is, if you have COVID, what's your prognosis? 3 types of prediction models. And now how many months are we there? 9 only. And already in the first few months, we had so many papers to go through, 50,000 papers to go through. And already there are more than 160 or 70 models to date predicting some COVID-related endpoint, sometimes of data sets of only 20 people, because we can. So that now we're living in 2020, having a situation, and still we have so much development. And I think, if I'm correct, I misphrase my own research right now, but I think only 1 was validated of all these 170 COVID-related models.
Yeah, actually, go on.
Now, so what has changed over the years? I think it only has getting worse, and that I'm glad actually you pick out that series right now, because it's now perhaps even more important than it was in 2009. Still.
Yeah, I was actually going to say the only good thing about everyone creating their own models is that we're so busy creating our own models that we don't have time to use other people's bad models. I would say that that's our main saving grace.
That is under the premise that your own model is good.
Oh, no,
And
no,
it's better
not
than,
that
of course.
premise. At the very least, that you aren't going to use two bad models as opposed to just one. So at least you'll have that you'll at least it'll be on internal data.
Yeah, but that's a good point. I mean, we are not developing, because if we do, we don't need to publish. We're not developing prediction models for ourselves.
Mm-hmm.
And perhaps if you do, if you only develop a prediction model from the data, in my case, from the UMC Utrecht, and I'm developing a prediction model on my UMC Utrecht patients, and I'm trying to apply it only in my UMC Utrecht patients, that's okay. But I don't need to publish that model then. Because if you do, it's in the open. And why do we do that? Is to have other people learn from that data, from that experience, actually, not only learn it, but to use that model also in their patients without having to redevelop it. Of course, that's the idea behind science and about publishing experiences and data, so that not everyone needs to repeat everything for themselves.
That's actually that's an interesting bit, because I'll be honest, I always thought that sort of medical statistics, when it comes to predictive models, that essentially it was an instruction manual for how to create your own. So I took the opposite sort of tact, where there was the idea that, and maybe it's because I work a little bit more on the personalized modeling. So essentially developing personalized time series. So essentially you describe the process, and then you show that the process generally worked on this. But that's interesting, because I think there is
but you
this.
do it also that others are going to use that.
They'll use the process. They won't use my model.
Yeah, okay, but but if that is the case, now take the framing and risk model. I understand what you're saying, and I like that idea as well. But take the framing and risk model. It's the way it's used in many countries to use for prediction cardiovascular outcomes in 5 or 10 years, and to make a decision on whether we should put them on cholesterol lowering or blood pressure lowering drugs or lifestyle changes, preventions. The idea is that framing a risk model is useful not only in the little village Framingham at the time, it still exists, quote unquote little, but also that in Boston it's used, or in New York, or even beyond the US. And you might validate paper 3, that model, in your own setting without repeating that whole process, but rather see how well it predicts. If it predicts good enough, use it. If it does not predict, you might tailor it starting from that model and improve it a little bit here. That's called updating, which is also described, by the way, the methods for doing that in paper 3. It's easier to tailor that model than to repeat that whole process, because repeating that whole process also requires that you have, again, a large data set with the same structure, well organized, well developed, that data set, no biases. So if we constantly need to repeat the whole process that you did with your model, oh my goodness, how much data do we need then?
Yeah, that's a really good point. And especially other ones that you mentioned, for example, SAPS, SAPS, the SAPS score, the Apache score, things like that. Obviously, those are meant to, you take them, you plop them down on this new clinical setting, and it's expected to just work as is.
With one more subtlety, Glenn, test them, see whether they are accurate enough. They don't need to be as accurate as in the original development set. That's also a mistake that what is often seen. Every developed model is usually working a little bit less in another data set. That's logic, because it's not fit on that data set. Developing a model means it's optimally fit, maximum likelihood, but it also applies to data science approaches even more. With machine learning approaches, they are perfectly fit on that data set, but they almost always behave worse in another data set. But it doesn't matter. If it's good enough if it's fit for your purpose, it's okay. You don't need to compare it with the development set. I think that's a misunderstanding, what people too much do. Because, it's worse than in the development set, so it's less useful. No, it's your decision if it predicts well enough. It's the consequences about the prediction. If you're happy with those predictions, if it's accurate, apply it. So I'm not saying that all the models that you mentioned are, when it's developed, apply to your setting. No, what I prefer is, but you need much less data than for development, is check how accurate the model behaves in your data set. If it's good enough, apply it. If it's not good enough, see whether you can easily update it with intercept adjustments or based on hazard adjustments, or perhaps even coefficients and predictor weight adjustments. And therefore you can very easily improve your models and already get there where you want to be with that model. So you don't need to redevelop it, only you need a little data to update it to your local circumstance, your local setting. And that's, I think, how the prediction scientific prediction model process should be. Large data set, people develop it with good studies and with good knowledge of the data, of the studies that led to that data. But you need a bigger data set to develop it. You need a much smaller data set to validate it. Tailor it to that circumstance if you're not happy enough. And then ideally, you check whether the use of that model truly leads to changes in the behavior or the decision-making of physicians, healthcare providers, patients, to see whether they truly have better patient outcomes. That's, I think, the ideal process that we should do.
Yeah.
Sorry for the long answer.
Yeah. No. Longer answers are why we're here. That's why we set up the time for this. Yeah. Two things real quick before people get a little bit confused, because there is, I think, a little bit of a different terminology where I actually tend to use and prefer the medical statistics terminology, where validation is usually referring to an external data set, usually as external as possible, maybe even a different clinic at a different time. In machine learning, of course, there's the training, there's the validation, the test set. So the validation set that medical statisticians are usually referring to is something much more akin to the test set that machine learning scientists are using.
Science, exactly. Yeah, good point. The answer is yes. And what we also use the term internal validation. We used to use the term, actually in the series we do, we refrain from that because we wrote a few more series after that, which is called, for example, the tripod statement, the reporting of prediction models, and also probust. And therefore we indeed rather do not use the word internal and external anymore. Validation means, as you said, testing in the machine learning world. Somebody developed a model, or including yourself, and you used a totally different data set to test the predictive accuracy of that model. And with internal validation, we mean, and that's the same, I think, the same wording as in the machine learning world. We simply mean that in the same data set as you develop the model, you use statistical approaches, testing, retesting, like bootstrapping, or some people use split sample. We don't like that. But like statistical approaches to do that, resampling approaches, let's use that word, resampling approaches, no new data, only your own data, to optimize, to see whether the model is too optimistic or overfitted.
Yeah, actually, I would also say that I preferred the earlier way of doing it, maybe because I'm getting older, but I like the idea of essentially putting qualifiers in front of the terms that you're using, because also, in addition to internal external validation, there's also, for example, temporal validation, where essentially you could be within your same site, but you're moving down in time. And that's, and I just like the idea that essentially you can add qualifiers and it just reminds you to think about explicitly what your statements are.
Very good point. Yeah. I agree on that.
Yeah.
And you even have, I think also in that series we use that term as domain validation, for example, or setting validation. I'm involved a lot in that. Is, for example, a prediction model that predicts, let's say, the presence of pulmonary embolism that was developed in acute medicine in a hospital. We simply evaluated that in a primary care setting. It's a totally different setting, totally different, almost domain, but you can do it. It's simply validate. That's called domain validation because it's a totally other target population than from which it was developed. And we also developed models in adults, and we validated and tested them in children below 18 years old. even though they were not included in the development set. That's also a kind of validation, but adding an additional word before the word validation, that helps very much. I like that also. Tempo validation, domain validation, setting validation, and all forms of external validation, in fact.
Yeah, I think it's also just good to generally remind people that these terms are concepts, and that when you have essentially these terms, while it's very useful to be using the same terminology, these are not some ossified religious text that must like never deviate. You can always be adding to them, thinking about them more. And that brings another bit up about this paper series that I actually found it very good. When I first went through this as a doctoral student, what I did is I took it and essentially I created checklists from it, where it's just different ideas, different ways that you can validate, ways that you can check. And it isn't just for saying, oh, I would be able to do these if I had more data. You can take these and apply them to your internal data set to start pre-testing some of these ideas. You can see if you have a really big data set, and I tend to have those, that like, well, if I temporarily divide my training data, and I train the model in one time period and predict it on another, do things start falling apart soon? And I think that's a very good way to start warning, like, are there some like inductive steps and inductive problems? And so I like this, that even if you don't have access to you don't need access to data set A, B, or C. You can basically say, depending on how much data I have, can I make sort of a judgment call where this is still not breaking down or this is still working on any given way that you can slice the data? I think that this helps you sort of identify different ways that you can slice the data and validate it.
Indeed. Yeah, and but yeah, you say that the crucial words you just said, it depends on the amount of data you have. I mean, we are now a little bit now, I mean, anno 2020, in a little different era than we were, but still, the majority of medical data sets on which models are developed are small, relatively. And if you don't have enough data, then using that splitting of your data sets sounds so appealing, but the disadvantage is that the data set on which you develop the model also becomes smaller. And I mean, smaller number of records, a number of individuals, whereas many people still develop models with a huge number of columns, which is the predictors or the input variables in the machine learning world. So you have limited number of records, individuals with a huge amount of input variables or predictors. And if you then also split such relatively small data set, then you are losing power, statistical power, of course, to develop a proper, robust, generalizable model. So I always keep on warning on that. Yes, in principle, that's good. Don't do random splitting, but rather in time, the older data set for developing and the current data set, the data set most close to current time. The temporal validation, that's good in principle. So you know how the model would work right now, closest to your current time, but only if you have enough data for the development left. And some people do, if you have thousands of records, but still the majority of data sets where models are developed on, in medicine at least, is very limited, relatively limited, I should say.
Yeah, and I guess that's a good segue to the issue of, it's not just how much data you have, but the nature of your outcomes. So essentially, you could have, if you have 10,000 patients, but adverse events are rare, and this is the main thing, that adverse events by definition are rare because humans tend to live, essentially you could have a data set. It'll take your example of random cuts. If only 10% of your, let's make it more realistic.
That is already big, 10%.
Yeah. It's like, and honestly, when you're talking about something like COVID, you're talking about, for example, 1%, 0.5% of your data. So say 0.5% of your data actually has the outcome of interest, which means, just for people doing the math, 99.5% do not have that. You split your data randomly. I bet you that with high probability, many of your models actually predict that something will never happen because there's literally no examples in the data.
The noise prediction is huge. Yeah. And Glenn, to add something, it's not only the number of events we're talking about, but it's also in relation to the number of input variables or predictors that you're studying. So if it's only one predictor, but then it's not a model, of course. But if it's only two predictors, that helps. But usually people still, and I understand that reflex. I've been there as well. Oh my goodness, I have a data set with 40 variables. Let's see how well they connect to my outcome, not only by one by one, but also in combination. Yeah, you get way overfitted models. So it's not only the number of events, but in relation to the number of predictors, candidate predictors that you are studying for inclusion in your model. Yeah.
Yeah. And then again, there's even further dimensions on that where, for example, if the nature of an outcome is different. So for example, the clinical nature where you can have a clinical death, but if it's because they were in a neural ICU versus a wound unit or a general ICU where this data, even if it is, even if it's one type of event that in practical clinical terms, and this can apply to non-medical domains as well, where there are subjective differences between these that aren't even captured by the data. And so your data set can come extremely small very quickly, no matter whether it's big. And when it's small, it's even smaller than that.
If you think that these outcomes are different and have a different kind of underlying association with the predictors, then your data set becomes much smaller than you thought it was.
On a practical note, so I guess this is probably something from I believe paper 2, paper 2 on developing a prognostic model. That we talked about, model selections. We've talked about variables. If you have frequently the number of predictors you can have vastly outweighs, for example, the number of like events of interest that you might have. And one of the topics discussed was whether or not it's good to do forward selection. How do you select a model? It's all an open question. That's it's one of the big adventures in data science and statistics where the selection of a model is not set in stone. This is cool for.
Yeah, and also my answer does not mean that it's set in stone. First of all is I think we need simply to realize, and that's already a big benefit if we understand that process and realize that what the consequences are. I think we all understand that if you have a low number of events and you start out with a huge amount of predictors relatively to the number of events, and whether you apply a forward, backward, or anyone else, but particularly the essence is if you use the outcome association with the predictor. So if you use your own data to select those predictors, then you need to realize, but I think we all feel that deep down in our gut feeling you got, that if you have simply too many predictors, forward or backwards, you will end up with a model that is very much tailored to that specific data set. And we all have a gut feeling that we know that if we would apply that to any other situation, then you will definitely have you'll see an overfitted model with much less predictive accuracy as in that original data set. So what we say, if you have many predictors and limited number of events, that we talked already about, that apply a kind of internal resampling process to see how much the optimism is and adjust your model for that optimism using shrinkage or penalization techniques. If you have, let's say, enough predictors relative to the number of events, and let's not get into detail what is enough, that's hard, but very recently, actually last year, I think Richard Riley et al. And Maarten van Smeden, together with myself, wrote a few papers, Statistics in Medicine, on the number of events needed for model development, both for dichotomous outcomes and linear outcomes. But let's say you have enough events for the number of predictors, then personally I prefer, but I think most people, is a kind of backwards, because with backwards you at least kick off with all the predictors, all the information you have, and then all the correlations between these predictors are immediately included in that model fitting, and then to see whether you could apply model reduction techniques without losing predictive accuracy. And as soon as you see that you will lose a predictor, but that you would kick out a predictor and dropping too much in the predictive accuracy or the explained variation of your outcome, a little technical, then stop and put that variable back in, and that's your final model. So I think I would prefer that method rather than the forward selection. And then the third situation, if you have way too limited data and too many predictors, don't use your data set for selecting predictors, not forward, not backward, but simply use knowledge and experience and clinical relevance, or perhaps even, can we measure the predictor anyhow outside a specific clinic, or can we predict it in the settings we developed the model for? Throw them out and then only fit that model with the predictors that you have pre-selected, not using your data, but using common knowledge or the literature.
Yeah, I have to say, way number 3 is the one that seems to ring truest for me personally. Where
I understand.
Yeah, and obviously some of that just comes with experience, and also just trusting my gut of how knowing to. And that doesn't that third way doesn't actually mean that you throw the first way or the second way out the window. It just means that third way means, like, for example, here's where I'm going to start my backward selection. Just very quickly, for those who aren't as familiar with forward and backward selection from a statistical perspective, we're either talking about essentially we take basically all our features, or a very large set of features, and we remove them based on whether or not there's been an assessed level statistical significance or some information criterion, and that if they are not sufficiently correlated with the outcome, that we remove them. And I guess, and then going forward selection is essentially saying we start with a null model and we try to build. And of course, let's just quickly knock out some of the ideas with this. Issue with forward selection, of course, is that it means that you're effectively dependent. If a new variable is going to come in, it must at least have some very large univariate relationship with the ultimate outcome. So I think that it puts at risk if you have a variable that's very important, but it depends on correlation, something like a Simpson's paradox scenario, that essentially a forward selection is probably apt to ignore that. Backward selection is actually a bit interesting to talk about backward selection from a statistical and p-value perspective, especially for prognostic and predictive models, given that a lot of the field, by the time they're doing predictive models, have essentially thrown a lot of the basic statistics and p-value type of intuition out. But maybe it'd be good to talk about that, at least for a minute or two, that if we were developing a predictive model, but instead of, this is what interests me from more of a machine learning perspective. I'm used to when you develop a predictive model, you're generally trying, and I do probabilistic machine learning, so there's a statistical element, but the idea that for that model, you're not going to be selecting the variable solely on the prediction metric. You're going to be doing it due to the actual statistical analysis of whether or not effectively they're correlated. Which I think is an interesting thing. It's sort of a two-step process, whereas a lot of other machine learning fields, just they keep it one step and they just tune it to that particular metric. Should we talk about that a bit and its implications?
Yeah. Okay. And what sense? What's your quick question?
Oh yeah. The actual question. So when we are selecting these models based on the statistical significance of the correlation between the predictor and the outcome, what are the types of problems? And we'll just do backward selection to keep this straightforward. We'll go back to keep it straightforward. What are the types of errors that you start seeing? What are the types of model problems that you see by using a statistical correlation at the second step, as opposed to just directly modeling improved predictive accuracy?
Yeah, that's the good thing. That's also the difficulty with prediction models. What do you want the prediction models do? That is, that they accurately predict. That means the calibrate, we call that the calibration measure, so that the predicted probabilities are equal to the observed outcome frequencies. And you can never do that on the individual level, not so easy, because each individual has 1 or 0, if you talk about the dichotomous outcome. So you need to do that on group on groups, but that's the idea of calibration, is the predicted probability equal to the observed outcome frequency, to the real probability. And the other one is, how well does it discriminate between people with the outcome versus people without the outcome, without the event. But the backward and forward, actually any statistical selection process, not any, but many, is usually on indeed correlations, on statistical parameters or information criteria. So what we, and that's because these are usually the most robust ones. With the maximum likelihood estimations on the log likelihood, so they are very much reliable, and it's a very good approach to use. Nevertheless, you always need to test and to check whether the final model with the selected variables, whatever forward or backward, based on that correlation or on the maximum likelihood or any other information criteria, that final model still is accurately predicting and also discriminating enough, and ideally on a test data set. And we call it a validation data. But let's call it an independent data set from which you developed it. That's what you need to do. And now, if that idea is is sinking down in the methods and in approaches that we do when developing and validating prediction models, whether it's using machine learning or prevailing statistics with backwards or forwards or any other variable selection, then I think we have gained a lot if that process is simply inherited. And that the fallacies that you have with backward selection or forward selection, because you focus so too much on only on the correlation or the statistical correlation, will be then double checked whether you lost somewhere in the predictive accuracy, in the calibration, or in the discrimination. Now, that testing on calibration discrimination is not frequently done. What I see, particularly is, and that's no offense whatsoever, because I also see it in the prevailing statistics, is somehow, don't ask me why, but probably because it was pressing buttons in statistical packages, is that the discrimination, the C index, the value of discrimination, is quite well and often done and reported. We saw that in prevailing statistics. In the prevailing statistical literature on prediction modeling, we saw that the C index is increasingly over the years well displayed and well reported. The calibration is very poorly reported, even in the prediction model papers with prevailing statistics. And I see the same happening now again with the machine learning literature. Somehow the C index or some measure of discrimination or classification is reported and is done, but they forget, to me, and I think to many of us, the most important aspect of a prediction model is the calibration. Is it accurately predicting what you want to predict? And that's not so often reported. So they do a lot of techniques with variable selection and internal validation and testing, but they forget to report or to check whether the model predicts the reality good enough, calibration. So if I get that message across with this interview, every model developer, do not focus only on the discrimination, the C index, but also on whether the model predicts accurately, the calibration, then we have gained a lot.
Yeah, and I have this for anyone who just tuned in or re-woke up in the middle of the conversation. So what we have is we're distinguishing between the calibration of a model, which must be checked, and the discrimination of a model. Discrimination of a model being the ability to distinguish between, I guess I would say, two feature sets that will have distinct outcomes, or in this case, two patients who are likely to have clinically distinct outcomes. And then the calibration, which I believe is pretty much what it sounds like, which is where is this actually following along what our prediction is. And I also view the calibration as related to that topic that we brought up at the beginning, which is when you bring in a new predictive model and you look to see if it's calibrated to new data. And that's sort of your metric for whether or not you need to be adjusting a new model. What did I miss?
No, you didn't miss, and we kicked off this answer about the relation with statistical correlation with variable selection, forward or backward, and that's of course statistical correlations is related to the calibration of the final model and discrimination of the final model, but it's not a one-to-one association, unfortunately. So using the statistical correlations for variable selection with prevailing statistical modeling or machine learning statistical modeling, I understand that it's okay, but do not forget to also take the next step to see whether that final model, regardless of your selection process, variable predictor selection process, whether that final model in an independent data set predicts accurately, calibration, and also discriminates well enough. if it's fit for purpose, the discrimination well enough in that independent data set. And let's have that rhythm always there. Yeah.
Cool. Yeah, actually, one topic that I wouldn't mind circling back around to was on the issue of validating on new data sets. The idea that it's said in the papers that if you have a choice between taking a model and applying it to a new data set and recalibrating that model, that it's preferable to essentially trying to redesign your model from scratch. And I think that this is an interesting idea. I think that it is certainly valuable, especially as a model development process. But perhaps instead of just taking that at face value, we should discuss it a bit. If so, let's say you've developed a model at your hospital, you sent it over to me. I have a new set of patients, and I say, okay, I'm testing the predictive accuracy, the calibration of my model, the discrimination of my model on this new group. It's discriminative.
Of my model, you mean?
Oh yeah, your model. Yep. Yeah, your model. Yep. And now I see that it is, for example, discriminative, but it is not calibrated. What is the next step? How do we go about this?
Yeah, I think this is very frequent. That's actually almost always the situation. You're lucky if it's just with this a good enough C index discrimination and a good calibration. So I have encountered it a lot. And what I would do is not immediately take in my own data set to start redeveloping my own model from my own data set. Provided, of course, Glenn, that the original data set was also not a very small one, because if it's a very small data set, you know already it's too optimistic, don't even try validate it, of course. Therefore, we developed Probust, by the way, the Probust tool on www.probust.org. You can find it where you it's a risk of bias tool to judge whether your model has face value, but also is overfitted or not, and should be applied for validation processes. But provided the data set, the development data set, my data set, because you are validating my model, but if my data set was good enough, was big enough, we had a good model, well conducted, we penalize it, and you are applying it, and you find poor calibration, and your data set is not 10 times bigger than mine, but let's say it's equivalent or perhaps even smaller. Usually validation sets are smaller, not always, but very often we see that. Then please suppress your reflex. You find a poor calibration of my model, the Moons model. Suppress your reflex to develop the Glenn model, of course. Colopy is your last name. Yeah, so suppress that reflex for a minute. Please first not to get the Moons model out there in the atmosphere. That's not what I'm meaning here, though. By the way, I just want to get out of the way.
I was just going to say very quickly, I only name the model after myself if it's any good.
But so don't do that. So suppress that reflex. Don't immediately develop a new model, but rather check whether you see, because that miscalibration you're talking about is very often simply an intercept change. You can see that on the calibration plot. If it's below or above the diagonal line, you know, it's by definition, it's an intercept problem. So just adjusting the intercept or the baseline hazard, depending on the type of prediction model you have, you can fit the job, fit that gap, and you make it well calibrated on your system. The only thing you needed, what was the original intercept or baseline hazard, and what is it in your data set, and there are statistical tricks and formulas how to do that, and you can do the job. Sometimes it's actually a little bit flipped, so that the calibration slope is not 1, because 1 means perfect calibration, but it's a little less. Usually it's less, 0.9 or 0.8. Then that means that the original model was too optimistic, overfitted for when you apply it to your data set. Then usually it's a slope thing. Now, slope means it's a regression coefficient or a predictor weight thing. So after some adjustments of the original predictor weights or regression coefficients, you see that you actually can make your model, the Moons model, well calibrated to your data set without developing a new model. So that means that the Moons Colopy model is now not based only on the Colopy data set, but it's actually based on the original Moons data set, combined, even though you didn't have the data set, but via the regression weight and via the intercept, it's now based on 2 data sets. So it's based on more data than it was already. And if you would have developed your own data set on your, it would only be based on the Colopy data set. And that, I think, is an unfortunate, a lot of people do. I did it myself as well in the past. A lot of people do, but I think it's an unfortunate way of dealing with scientific evidence or scientific data. If somebody already did quite a good job, don't throw it immediately away and take it for granted, and just repeat it in your own data set. Because it's simply throwing away existing evidence and perhaps indirectly even throwing away existing data.
Yeah, and I'd also say
the ideal of method, by the way. Now, Glenn, just 1 minute. The ideal would be, of course, Karel, give me a call. Karel, I have a similar data set. Can we bring these 2 data sets together and make it in a bigger IPD data set? And let's see whether we can fit the supermodel from the 2 data sets combined, or even more data sets.
Yeah. And of course, we'll have to stop that. We'll have to nip that one in the bud, because too many conversations go into hierarchical modeling, and we of course we can't allow too much hierarchical modeling.
No.
But yeah, no. And I was just saying, since we're even discussing on the scientific issue, I think that it might be worth reflecting on sort of, there's a good scientific reason to believe, for example, that if a model is miscalibrated, check the intercept first. So for example, my hypothesis on this has always been that most things, correlations seem to go in the same direction, unless there's something like fundamentally different about these models, like these are literally 2 distinct patient sets. So many correlations seem to go in the same direction, but sort of the general acuteness of, for example, a patient population might change. So that was always my interpretation of saying you can always adjust the intercept and look at the intercept first before fiddling too much with the slopes.
Good point. We say that too. And that's paper 3 we're talking about now. It's somewhere in paper 3, or at least we refer to the more in-depth papers. Indeed, I'm always inclined. You see that also on the calibration plot. If you look at the calibration plots, it gives you already the indication, is it an intercept or a slope thing? And always starts with the intercept adjustment, because you fix a lot with that. We have written, I've been involved in quite a few papers that also showed this, what you said, that fixing the intercept based on hazard, depending on the type of model, already gives you a lot of solves a lot of your problems of miscalibration.
Yeah, and I guess one other thing that I wanted to cover about the idea of variable and model selection is obviously, because we're going to be having the Zauerbrei and Royson conversation a little bit later. You cover fractional polynomial models in this, which I think are interesting both from a biological and just sort of practical scientific perspective. I think that they are very good alternatives to essentially imputing linear forms on models, or worse yet, step functions of some sort, implicit step functions or dichotomization on a lot of these models, because I don't think those reflect most biological reality. But I also saw on this, I think that the fractional polynomial discussion, regardless of whether you're going to use, for example, fractional polynomials or maybe a Gaussian process method, that there's this desire to move away from really hard-coded functional specifications of your predictive models. Similar things with splines, where effectively splines are nice ways to sort of smooth through the data, but you shouldn't be interpreting every little wiggle in a spline fit, because obviously some of those are just functions of the data. So where I want to go with this next
is... you put knots on that,
Yeah.
Therefore, you put knots on these splines and the number of knots that you allow as a particular spline, But this is a good topic. I mean, I would love to talk about, but this is a good topic indeed for Patrick and Willie. To cover that with them,
Yeah, but I guess maybe just to discuss it a bit more broadly, that one of the big issues here is that predictive models tend to fail if the functional form that you're giving them, and by functional form, I just mean if you're calling it a linear model or calling it a quadratic model, it really better be a quadratic model, because in the tails, for example, things go, polynomials are nicely sort of behaved where you have your data sometimes. But of course, in the tails of any polynomial model, they do extreme things, as polynomials want to do, as we learned in high school.
I think, I think therefore people that prefer the spline approach like to go for the splines because they behave better in the tails. I think that's the reasoning behind it for not moving to fractional polynomials, FPs, but rather to the RCS, the restricted cubic splines.
Yeah, and I'd also just say for anyone,
But
because I go on.
yeah, I just wanted to say a good point. And now we're flipping back to paper 2, where you talk about development, and it's not simply including the predictors into your model. That's actually the essence that you're saying, but that the functional form of the predictor with the outcome, and ideally not in the univariable space, that predictor with that outcome, but in the multivariable space. So that means a backward selection approach, by the way, because otherwise you couldn't do that. So the functional form in the multivariable space with the outcome of the predictors, with the outcome, that's extremely important, because way too often is that there are prediction models developed and they didn't even check this, and then they probably have misimported predictors or included predictors that could be much better in their predictive sense than the way they include it, and that's usually simply as a linear term. And that's a fallacy that way too many people indeed make. And it's a good point. I haven't checked it yet how often this is covered well enough in the machine learning world or in the AI world. I'm not sure. Do you know that? Is this a feature characteristic that's on top of their brains that they always check that, these functional forms?
Yeah, I would say, yeah, I mean, for people who sort of follow the maxim that your model should always be describing the data generation process. So when you take that as your first step, then you say, well, is the data generation process linear or polynomial? And the answer is, of course, it's none of those. It's never, there's nothing on Earth that really operates except, I don't know, planetary motion on some way, according to these like very distinct finite degree polynomial functions. And so I know, for example, a lot of the Gaussian process work, for example, one of its main benefits is that it doesn't impute an explicit functional form. It's implicit from the data itself. And so it basically, one of the things it is, you will have feature selection. It's in the covariance structure. But what that saves you from is having to do this polynomial feature selection and sort of this feature wrangling. So it's sort of like you trade one for the other. And then, so I think that number of degrees, for example, of your polynomial is an issue. And actually, even in practical terms, for anyone who's thinking, oh, well, these sort of polynomial models are just, they're old, no one uses them anymore. Not actually true. I actually had an application recently where my data set was quite small. I only needed basically slopes and like directionality. And I had to go back all the way to just basic polynomials, doing some fits and some checks. And, the basic issues with polynomials, whether they behave in the tails and things like that, is very important. And so, it is, I think a lot of machine learning work, when you're trying to abstract with some of the issues with feature selection, one of the easiest things you can do is try to not be imputing these hard forms and let it be a little bit. The non-parametric, Bayesian non-parametric world, I'd say, is pretty well suffused with these types of things. So I hope that answers the question. Yeah.
Yeah, it does. Yeah.
Since obviously this is we're talking about the scientific aspects of data science and statistics, and science is a largely inductive process. I thought it might be good just to explain why these issues are not just applicable to medical science, but general data science. We cover the issue of applying your data set or your model to new data sets. And one thing I think we could just discuss briefly is, why does a model's performance change from one to the other? We have ideas like, that the model fit is different, the parameter selection, but there's also just more fundamental differences in data sets. For example, they're derived from different processes. Maybe it'd be good just to end on that discussion, where we just talk about why it's important to use judgment and really understand your data generating process when figuring out how to move your model forward.
Yeah, that's a good point. That has to do with the what we talked about before. Is somebody developed a model, and then you apply it or test it in your data set, validate it in your data in your own data set, and a different data set, and then you see different calibration or different discrimination, and we've talked about updating intercept and regression coefficients, and now you're asking me what are the more generic causes that could deal with that process. Now, first of all, for starters, is it doesn't matter what the exact cause is, you see that it miscalibrates somebody or misdiscriminates or lower discriminates, so you have to deal with that. Now, what could be causes, and that helps to understand the data generation process. And first of all, it could be simply that the incidence, so we talk about prognosis, so it's incidence. If we talk about diagnosis, it's prevalence, of course, but that the frequency of the outcome is simply different. And I have encountered it a lot with cardiovascular prediction models developed in the 80s or 90s, and then I apply it in my current time, and then I see much less events, and that's because that care has improved. More preventive management, a better lifestyle, better treatments, whatever. So that's a reason why you have lower outcome frequencies. So that's a cause, and you see only in your data the lower incidence, but understanding that is important. So you need to understand where your data set come from and also which time period. Another what is simply the case mix variation, is that it's simply a similar but different population than the original one. So you have different case mix variables, which means that, and if these case mix variables are included as predictors in the model, then it might be covered. But if it's a case mix variance with predictors that are not in the model but are important, yeah, that means that they were missed in the development and play a role in the validation set. That the associations between the predictors have changed over time. So it's not only the overall incidence, but it could also be that the associations have differed, or that the predictors are measured differently. For example, that they used blood pressure measurement with auscultation, with the hearing, the conventional method, and then the new data set is with automatic measurements. It's a simple example, but the way predictors are measured is important. The way the outcome is measured is important. It could be different, not with overall dead. That is dead. It's in every country the same. That is dead. Wait 2 minutes, and you know that something, 4 minutes, and that is dead. But if it's an outcome that requires some kind of subjective interpretation to determine outcome present, yes or no, that could be in the development data set. Others are different than in the validation data set. Difference in measurement error, so to say. So that all are causes that are the reasons why the model behaves poorly in your data set. Yeah, and indeed, it's a good point. Let's stress this. Therefore, using the human brain, understanding the process of the data generation and the time period where the development data came from and your data set comes from, that is almost a necessity, a requirement to interpret the model in your data, in your setting. And that's a good point. I'm glad you brought this up, because I forgot this. We stress this very much in our series, but it's usually forgotten by a lot of prediction models. They simply have a data set. They don't even ask where the data set comes from, and simply analyzing and finding associations and coming up with a model and validate that model or test that model. But that's usually not enough. That can bring you into problems, particularly if you want to generalize that model to other settings. You need the understanding of the data generation process. And I didn't speak about missing data even, and how they dealt with missing data. That's my middle name, Karel Moons, because that's my hobby, dealing with missing data, but let's not discuss that.
All right, we'll put that in a box for another time.
Yeah. I have a series data as well, by the way, in the Journal of Clinical Epidemiology.
Oh, really? Oh.
Yeah, that's something else.
Cool. Sweet. Well, I hope everyone has enjoyed this. I've certainly enjoyed this conversation. For those who did not read the series in advance, the series along with the tripod links will be in the video description below. So definitely read it. I think it's extremely helpful for early career data scientists. It doesn't matter if you're in medical statistics or in finance or in supply chain modeling. The process that they describe is easily understood. They use models that you can easily understand, so you can stick with the concepts. And it's a very good checklist to start understanding how you should be sorting out your work and deciding how to develop the entire process of predictive model, because it isn't just fitting and you're done. There's a huge process before it. There's a process after it. And I think that this is probably one of the two best descriptions that we're going to have on that issue. So the other one being the NIPS paper, I think that I might have mentioned at the beginning. But Karel, thank you so much for your time.
Thank you. And now I'm glad also, that's a good ending, that if you have done all your research, you need to report it transparently, because without transparent reporting, others can never use your model and will not use your model. So you can be angry, but you should only be angry at yourself, because transparent reporting is the essence of using the model by others. And that's where we developed tripods. So it's good to end with tripod. And tripod comes in the whole process at the end. People think, at least, because that's what you need to report. But personally, I use the tripod checklist already at the beginning, because if I know what is demanded to report, then I need to make sure that I also get that information out there during my research. So the tripod checklist is also very helpful for everyone who is in the prediction modeling world to use that upfront as well. So as the PROBUS checklist is a risk of bias checklist of prediction models, it's very useful to use that upfront. And it doesn't matter whether you're predicting the medical outcomes or non-medical outcomes. It doesn't matter whether you use prevailing statistics or machine learning or artificial intelligence methods. It doesn't matter whether you're predicting in cardiovascular, cancer, or orthopedics. It doesn't matter whether you use genetic predictors or non-genetic predictors. It's quite generically written. Of course, it has subtleties in the different domains, but it's largely applicable to all of these different domains.
Because it's about scientific rigor, I'd say.
Indeed.
Indeed. And that's why we use science on many things as opposed to just one or two things.
Good point.
Cool.
Thanks.
Thanks, Karel.
Thank you too.
Hey guys, it's Glenn. Thanks so much for listening to this most recent episode of the Philosophy of Data Science. I hope you enjoyed it. If you did, please consider leaving a like, a comment, and hitting that subscribe and bell button. We're a small channel and every bit helps. If you have a lab, a department, some students, or some colleagues who you think would enjoy this episode, please consider sending along. Again, every bit helps, and we really appreciate your word of mouth. Our next episode on the Philosophy of Data Science will be coming out 1 p.m. Eastern Time, Wednesday of next week, so we look forward to seeing you then. But if you can't wait to get more data science, machine learning, and statistical content, feel free to look around the rest of the channel. We have a large number of playlists, including things like machine learning for healthcare, ethics and AI, and things like that. So give a look around. There's plenty more content for you to enjoy. You can also check out our website to not only see past episodes, but what's coming up, and see who our sponsors are. Thank you to our sponsors for your support. Now, while the views discussed on the show typically range between extraordinary and mind-blowing, the stated views don't necessarily represent those of the host, our sponsors, my employer, your employer, the speaker's employer, or anyone else not saying those words. And as always, thank you so much for your time. I really appreciate it. See you next week.